I do it? Thursday. Thursday, June 9th, 6 o'clock class. We did the first two of these. By these, I mean the last 5 chapters. We did the first 2 already, disease and mechanisms of disease. So the next 3, let's take a look at non-specific defenses. Non-specific defenses. So there are actually 2 types of resistance. I know a lot of you have had A and P already, so you kind of know this already. 2 types of resistance, specific and non-specific. Non-specific is a general line of defense against any pathogen. Now remember, of course, pathogen is a disease-causing microorganism. So non-specific, any line of defense against any pathogen. Specific means specific resistance to specific pathogens. So that would involve antibodies. In other words, the immune system. The immune system is your specific resistance. So specific antibodies for specific antigens. We're not going to cover it, it's too big a topic, and so on and so on, so we'll just skip by it. So we will just do non-specific. So non-specific, the first line of defense is the skin. Obviously, it's going to be much more general than that, non-specific. So the skin and also the mucous membranes, I think I've said it to you already, but the mucous membranes are membranes covering the interior of body cavities that are open to the outside. These are cavities that might dry out because of exposure to the outside. So the mouth, the nose, the anus, the vagina. Also the urethra, although that's to a lesser degree, but those are the 4 main ones, and they're all covered by mucous membranes to provide moisturizing and to prevent drying out. So the skin, this is definitely a duh moment. Consider the dermis and the epidermis. The latter is covered by keratin. Keratin is a waterproofing protein. It's something that all land animals have. It had to develop when we all came out of the ocean. And obviously, there's a real danger of drying out, dehydrating. So all land animals develop this keratin. Now, we all have it. For mammals, we have it on our hair and our skin. Birds have it on feathers, and so on and so on. Plants have a similar thing. It's the wax. That's the cuticle. That's on plants. For the same purpose, to prevent them from drying out. At any rate, for us, it's keratin. So the skin obviously provides a physical barrier. Don't need to tell you that, but I just did anyhow. Also secretes perspiration or sweat, which is acidic. The acidity is around 4.5. And that's actually the same acidity as orange juice, as citric acid. So our skin's a little bit acidic, but it's not that acidic. But it's antibacterial. The acidity, acid in general, the nature's proteins. So that being the case, which kind of bacteria would be most vulnerable to that? Gram-positive. Remember what I've always said, if you don't know an answer, just say gram-positive, because it usually is. So then, yeah, so gram-positive, of course, because they got the most proteins compared to gram-negative. So those are the ones that would probably be danger. Tears and saliva also protect the mucous membrane. Saliva, of course, in the mouth. Tears in the eyes. I think I mentioned to you the other day the what's the membrane?
Conjunctiva.
What?
Conjunctiva.
Thank you, the conjunctiva. Thank you. I've totally blanked out. The conjunctiva. Yeah, the conjunctiva is a very nice breeding ground for bacteria. So the tears will help to contain lysozyme and will help to protect from bacterial growth. Totally blanked out on that. So oil and sweat produce An acidic environment, again, around 4.5 or so. Sweat and saliva, lysozyme, antibacterial protease is extremely common in our bodies, extremely common. And again, for the ears, same thing, they have lysozyme. So all of that would be the first line of defense. Second line of defense, I have here is phagocytosis, but in honesty, a better term would be simply biological. Because part of this is not phagocytosis. That obviously refers to macrophages. And it's there, but it's a broader defense system than just simply that. So the first line of defense, skin and mucous membrane. Second line of defense, we'll say biological. The third line of defense that we're not covering is, in fact, the immune system. So, phagocytosis done by macrophages. Macrophages are white blood cells. Not in this case. They certainly can be macrophages, are part of the immune system, but in this case, no. There actually are a category, this is off the record, called natural killer cells. The natural killer cells, they are macrophages, they're not part of the immune system. And the reason is because they're non-specific. They'll attack anything. So you actually have some macrophages that are part of the immune system, that are very specific, and some that are not. The inflammatory response. This is something I cover a lot in my A&T class. It's just a totally common type of response when we have damaged tissues. You cut yourself, bruise yourself, anything like that. When the tissues are damaged, the damaged cells release histamine and kinins. They both cause vasodilation. Now, vaso refers to the blood supply, circulation. Dilation means to expand or to swell up, like blowing up a balloon. That's dilation. So they cause vasodilation. The blood vessels expand, specifically the capillaries. Specifically the capillaries in the damaged area. The capillaries in the damaged area will swell up. The cell wall, not the cell, sorry, the capillary wall will become quite thin. Again, like blowing up a balloon. It becomes quite thin, and in becoming thin, the plasma leaks out of the capillary into the damaged tissue, which is the whole point, because the plasma contains healing factors. So kinins do the same thing. So histamines and kinins both do this vasodilation. So do prostaglandins. They're all just simply different chemicals, but they all will cause vasodilation, which means basically, even though inflammation is part of the healing process, we do overkill. We do too much. And the vasodilation increases the flow of plasma out of the capillary, bringing healing factors to the damaged area. So as I'm presenting this, it makes it sound like inflammation is part of healing. Well, it is. So therefore, you might wonder, you've always been told, put ice on the damaged area, take ibuprofen, take anti-inflammatories. And you might wonder, should you really do that? Yes, I live on ibuprofen. The fact is, we do overkill for the inflammation. So by putting the ice on, by taking the anti-inflammatory, you're going to reduce the inflammation. You're not going to eliminate it. There still will be some. So yeah, go ahead and do it. And there will still be enough of this left over to do the healing. So at least you can reduce kind of the uncomfortable parts. So macrophages come into the area because they always do, attracted by chemotaxis. The chemotaxis is the damaged tissues are going to also send out chemical signal flares calling for help. So the macrophages come in, follow the trail of these signal flares back to the origin, back to the damaged area, that's chemotaxis, and then does what macrophages do. Macrophages are an extremely important part of our immune system and our general defense system. The macrophages clean up the mess. And then after that, tissue repair begins. You've got to clean up the mess first, then you start repairing. All of that's inflammation. The symptoms are, again, you've got plasma leaking into the area. Soreness. Well, the soreness is coming from two things. One is you do have this fluid flowing into the area. Your skin will swell up and get tight. That can be uncomfortable. But more than that, this extra fluid can often squeeze or press upon nerve endings. You've got extra fluid in one area. So the nerve endings can become squeezed upon, and that's uncomfortable. That's soreness. It's usually not pain. It's just sore. Redness, particularly for fair-skinned people, the extra plasma in the area can kind of show up as extra redness. Swelling, yep, you've got extra fluid. That's going to be swelling. And finally, we are called warm-blooded for a reason. The extra plasma in the area will bring heat. That's why you put ice on it. So soreness, swelling, heat, got one. And redness. Those are the four symptoms of inflammation. Again, it's part of healing. It can be uncomfortable, it can have inflammatory, but it is part of healing. Fever. This is not part of inflammation, but I remember being too lazy to start a new slide. Fever is a systemic response. Now, the term systemic means the entire body. It's over the entire body. The inflammation is just localized. It's just in one area, whatever you damage. Fever is everywhere, your whole body. Systemic response, which raises the body temperature to try to kill bacteria. So think it through for a minute. What temperature do pathogenic bacteria most like? Think it through. Pardon me? Body temperature, exactly. Those pathogenic bacteria have to live inside of us. Otherwise, how do they cause disease? So body temperature, meaning 37 degrees or 98.6. Well, that's what the fever is. Think back on times, you all had fever. Think back on times that you've had a fever. How high did it go? Usually around 100 and maybe 101. And usually it would last for a day or so. Usually it's not longer than that. So if you are getting a fever for 100, 101 for a day or so, don't call the doctor. You interrupt his golf game, and he has other things to do. Basically, even though you're not very comfortable, you're sick. But your body is doing what it's supposed to do. It's raising your body temperature to a level where it makes the bacteria uncomfortable and they go away. That's what fever does. Now, if your temperature goes above that, if it goes to 102, 103, or if it lasts for more than a day or two, okay, that means you're losing. You're losing the fight. That's when you call the doctor. I still remember when I was in Africa, I did not take my malaria pills. I got malaria. It was an amazing coincidence. And my temperature did go to 104. So the doctor was not happy and kind of let me know that besides being sick, I was also stupid, which I was. But 104 would not be advisable. I mean, then you do need medical care. But the normal fever, 100, 101, yeah, you got a normal fever, wait for a day or so, it really should go away. If it doesn't, we call the doctor. But the whole idea, though, is to make the temperature high enough the bacteria go away. So it's part of healing.
So is it bad to take an inside?
I'm sorry.
Is it bad to take an anti-inflammatory?
Well, that wouldn't work on this. That wouldn't work on fever.
What about like Tylenol? Fever reducer. Fever reducer.
Yeah, no, it would not the same. It would not be bad for the same reason as the anti-inflammatory supplement. You're not going to really reduce it all the way, but hopefully by the time you even get around to it, it's already done its work. So now I would say no, take it if you have it. The Tylenol will work for a fever. I tried it once, it didn't work, but everybody's different. Antimicrobial substances. Now these are proteins. That's why I wanted to get away from my calling this phagocytosis, because quite a bit of this is not phagocytosis. Biological is a better second line of defense. Complement. We talked about that before sometime. A series of 20 proteins. And they can act in one of two ways. They're kind of a backup system. One is called cytolysis. Cytolysis, so literally rupturing a cell. The cytolysis. The complement itself can bind to the cell, the bacterial cell, and can kill the cell directly. It's not that common, but it does happen, it can happen. That's not the most common thing complement does, but cytolysis. The other main mechanism is opsonization. Opsonization. Opsonization is that the complement will bind to the cell. See, this is like when, for example, the cell, the bacterial cell has a capsule. So if you remember, the macrophage cannot bind because the capsule is too slippery. Well, the complement is way, way smaller than a cell, than a macrophage. So it can bind. It swarms around like a swarm of mosquitoes. You know, we're way larger than mosquitoes, but they can sure get us. And that's what happens here. The complement will bind to the capsule on the cell, and then the macrophage can bind to the complement. So you've heard me use the analogy before, double-sided tape. Binding to the cell, the macrophage binds to the complement. Like I say, the backup system. If the macrophage does its work, you don't need the complement. But in case the macrophage cannot do its work, the complement comes in. Interferons. These again are proteins. They are antiviral proteins. They interfere with viral multiplication by interfering with translation, with viral protein synthesis. Now, because of their ability to interfere with translation, interferons have been tested and used for cancer research. The idea there, of course, is your cancer cells are reproducing like mad. That means making new DNA, new proteins. So it was hoped that maybe this could work with the cancer cells as it does with the virus. In fact, it has not been successful. And I'm sure somebody's still working with it, with interferons, but by and large, most people have moved on to other things in terms of cancer research.
Is that another kind of complement?
I'm sorry?
Is that another kind of complement?
No, totally different. Interferons are different proteins. Yeah, complement's complement. But see, all of these are backup systems.
Right.
And again, non-specific.